We had to find its derivative. Now we're going to be given the derivative and we're going to go backwards and find the original function. So just like we had rules for derivatives, we are going to have rules to go backwards to find the original function. Here are 3 derivative equations. We're going to pause the video here for you and your groups to try to figure out what a possible equation could have been to get that as a derivative. So for A, you could have said 2x plus, and then pick your favorite number, say 13. For B, 3x squared is the derivative of x to the third. And then I'll say minus, I don't know, another nice number, 29. And then C, to get 4t as a derivative, maybe we started as 2t squared plus, and I'll pick another nice number like 7. So what's happening here is all of these constants at the end could have been anything, so we can just call them all plus C. Because regardless of whatever that constant is, it's not going to show up in the derivative. Okay, we're going to pause the video here for you to fill in the blanks, and then I will explain it all to you. So when we go backwards in math, it's called an inverse. So the operation of determining the original function when you're given the derivative is the inverse of differentiation. That inverse is called antiderivative. So a function f, and notice this is capital F, is an antiderivative of a function little f, that's the original, for every x in the domain of the original f. So it follows that if you take the derivative of the antiderivative, you will get the original function. So here's what that means. If capital F of x is an antiderivative, then f of x plus c, where c is any constant, is also the antiderivative. So that's why I kept adding c back up in our first examples. So for example, if we have x to the third, that's an antiderivative of 3x squared. If 3x squared is the derivative, the original function was x to the third, the antiderivative. Same thing of x to the third minus 5. If we took the derivative of that, we would get 3x squared. The antiderivative of 3x squared could be x to the third minus 5. Same thing with this plus 0.4. So it doesn't matter what this constant is at the end, it's not going to show up in the derivative equation. So the anti-differentiation process is called integration. Oops, sorry. It's denoted by the symbol, and it's like an elongated S. If you're going to draw that, it looks like this, which is called the integral symbol. The symbol, the integral of f of x dx, is the indefinite integral. Because we're not going to find any values, we are just going to find equations. The indefinite integral, so it denotes a family of antiderivatives of the original f of x. So last unit, before spring break, you kept saying, why is the dx there? Why is the dx there? So now we can see the reason. The integral of f of x dx means what is the antiderivative of the function with respect to x. Just like when we did dy dx, that meant the derivative with respect to x. When we got to related rates, it was the derivative of area with respect to time. So it matters what this variable is, in our case, this dx, because it's telling us we're going to be referencing the x variable. So what we're going to do down here for number 2 is just rewrite these using the antiderivative notation. So 3 being the derivative, if I take the integral of 3 dx, I will get 3x. For b, if we take the integral of 2x dx, we would get x squared. So what this is saying is if 2x is the derivative, what was the original function? If 3 is the derivative, what was the original function? So again, for the last one, the integral of 9t squared dt now, there's no x's, is going to be 3t to the third. So now on page 4, what we're going to do is write our basic rules of integration. Just like we had rules for finding the derivative, we're going to have rules for finding the antiderivative. So when you're given a constant, k, so the antiderivative of k, dx, is going to be kx plus c. We need a plus c on every indefinite integral because the derivative of that constant will not show in the derivative of the constant would not show here in this function. So we have to account for it every time by writing plus c. If we have the antiderivative of a constant times a function, we can take that constant out of the antiderivative operation before the integral and then just do the integral of f of x. The sum and difference rules say that if you have two functions added together, the antiderivative could be f of x dx plus the antiderivative of g of x dx. That you could split that into two separate antiderivative operations. Same thing with the difference. And now the very, very most important one today is going to be the simple power rule. How are we going to go from something like x to the 5th back to what equation would give us that derivative? So when you're given x to an n, to find the antiderivative, it's going to be x to the n plus 1 divided by n plus 1 plus c. Before, when you found the derivative, you subtracted 1 from the exponent. Well, now the opposite is we're going to add 1, and instead of multiplying by the exponent, we're going to divide. Everything is opposite. So here for number 3, 4, and 5, these are all constants. 1/2, 1, and -5, these are all constants. So the antiderivative of 1/2 is going to be 1/2 x plus c. The antiderivative of 1 is going to be 1x plus c. And then for 5, see how it says dt? So it's going to be -5t plus c. This d part tells us which variable you're going to use in your antiderivative. So what we just wrote was if I take the derivative of -5t plus c, I will get -5. If I take the derivative of 1x plus c, I get 1. If I take the derivative of 1/2 x plus c, I get 1/2. So now we're going to use the simple power rule in number 6. This 3 is the coefficient, so we can just leave the 3 there. The exponent is a 1. So I'm going to do 1 plus 1 for 2 divided by, and then the new exponent goes in the denominator, plus c. So we can always check if I have 3/2 x squared and I take the derivative of this, what's going to happen? It's going to go to 6 over 2x. And what's 6 divided by 2? That's 3x. Is that what we had here? It is. So our antiderivative worked. Just like with derivatives, you cannot take an antiderivative with an exponent, with a variable in the denominator. So we have to rewrite our exponent so that it's negative. Now I can do the simple power rule. -3 plus 1 divided by the new exponent. Now this term with the negative exponent will move back to the denominator. We get -1 over 2x squared plus c. This negative, we don't have to leave it in the denominator. It can be in the numerator like that. Same thing for the square root. We have to change the radical to an exponent. Then I'm going to add 1 to the exponent. So 1/2 plus 1 is 3/2 divided by the new exponent plus c. Now dividing by that fraction, I'm going to multiply by the reciprocal. And that's our final answer. 2/3 x to the 3/2 plus c. Now for number 9 and 10, these are using the simple power rule, but with the sum and difference. So what it's saying is, and we don't have to write this every time, you're going to do the antiderivative of x plus the antiderivative of 2. It works like that with any polynomial. Instead of separating it, we could just go down the term and take antiderivative each time. So for number 9, that's going to become x squared over 2 plus 2x plus c. This had an exponent of 1, so we add 1 to the exponent over the new exponent. The constant gets the x, and then always a plus c. So then for 10, I'm going to add 1 to my exponent over the new exponent. Add 1 to the exponent divided by the new exponent. Add 1 to the exponent over the new exponent. So each time this exponent gets added by 1, and then that same exponent becomes your denominator. This exponent of 2 gets added to 1 to get 3, and then that's the new denominator. So your homework is all of page 5, and it is practicing getting these antiderivatives. Make sure you can finish and get all of the right answers that are at the bottom of the page.